Hello and welcome back to Calculus 2, section 10.3, which is on infinite series. Previous two sections, we talked about sequences. That was our last class. And we said sequence is ordered list of numbers. Ordering is done through natural numbers, counting numbers. You can start counting at 0, you can start counting at 1, and then you can have the formula, the roster method, and then you also have recursion. We went back and forth. We defined all of the monotonic and increase, decrease, all of that kind of stuff. And we understood sequences, and those are just list of numbers. Hello, series. The rest of the chapter is on series, and we start with the definition. Series is a sum of the sequence. Series is the sum of the sequence, and the notation is summation symbol of an, where your n starts, let's say, at 1 or at 0, doesn't matter. And in many cases, well, cases that we are going to consider in our calculus course, goes to infinity. And I'm just going to point a purple arrow there and say infinite series. Infinite series. Do you have finite ones? Sure. Are they interesting? No, because they always converge, and you can always calculate those. If it's too many things, talk to Mike. He'll write something for you, right? If you have 10,000 terms to add, you're not going to sit there and add 10,000 terms by hand, right? You put that into some, right? Because there has to be a formula for it if it's finite. Remember, all of the numbers came from a sequence, and sequence is always ordered. Therefore, you can always program it. Always. 100% of the cases you can program it. If it's finite. If it's infinite, good luck. We'll see, because that's what the chapter is all about. So, finite one, finite series, in parentheses, boring, is going to be a series, something like a series of 3n minus 1, when n starts at 1 and ends at 5. 5 minutes ago?
Not even.
5 minutes? It's like get 2 lines. Exactly. So you have your n's. Your n's are going to march from 1 to 5. So you'll have 5 of these to add. And you're done. So the first one is 3 times 1 minus 1, and then 3 times 2 minus 1, and then 3 times 3 minus 1, 3 times 4 minus 1, and 3 times 5 minus 1, for the total of, that's a 2 plus 5 plus 8, no coughing, plus 11 plus 14, and that's a 10, 20, 30, 40, right?
You should have something like that on the exam.
Finite series?
Yeah.
No. See, it says boring.
That's okay.
What are we interested in? We are interested in infinite series, because infinite series can add up to a finite value. Infinite series can add up to infinity. So infinite series are the ones that we are focusing on, because those can converge or diverge. And today, you all have the piece of paper. If you just obtained this today, this chart, please talk to the people that are sitting next to you to see what things they wrote on it last time, because these charts were enhanced last time. Because there are sections, right, that you have to match to your, right? So today we are going to cover geometric and telescoping series, rows 2 and 3. That's in this section. But let's get there first. So infinite series is the title. And we are considering summation of an as n goes from, let's say, 1 or 0, doesn't matter, to infinity. This series can add up to a convergent or a divergent. So if you are guessing, it's 50-50 chance. Good odds, right? Now, that's only 2 out of 10 points, because the other 8 points are the work to get to this, right? So you have a 50-50 chance to score 2 points out of 10. Not a good odds, right? Last class, I also asked you to, right, and we saw some already, knowing this entire sheet is absolute a must. And we'll talk about that as we go along, why and how. So infinite series, very simple, sum of the sequence. And what we do here is we sum of the sequence, and we are just adding all of the terms, infinite amount of terms. And trust me, it's not a joke, it's not an easy task. A lot of thinking has to be put into this. Question. Sequence an is given by -1 to the n. That's a sequence, not a series, right? What is the roster form for something like this? Well, if n is equal to 1, you have -1, then you have 1, then you have -1, then you have 1, then you have -1, then you have 1, and it goes on forever like this, right? So what you see is a sequence of numbers. What is the convergence or divergence of this sequence? Well, you take the limit, right? And it ends up not having 1. So we label it as a divergent sequence. Then you look at this closely and you say, how about series? And this is why I am asking you to retire common sense, because it is going to hurt you greatly in this. What would your common sense answer be if I am looking at the sum of all of these?
-0.
0.
Oh, it's -1, +1.
-1, right?
Yeah.
Common sense is 0, but it's wrong. It's wrong. Now, what is the common sense? Well, you say if I am to add all of these numbers, right, this one and this one, when they add, they create 0, and then add this one and this one, they create 0, and then this one plus this one, they create 0, and if I go to infinity, I'm just adding infinitely many zeros. No, unfortunately wrong. So, retiring common sense in chapter 10 is probably one of the hardest things to do, to let go of things that, look okay, right? But then you have good examples with social justice, so you should be able to do that. Exactly, right? You retire common sense and you get all the stuff they come up with. So, what do we do and how do we deal with this? This. All right? So, through the course of our chapter 10, we will learn how to do this problem in 10.6 because that's what this problem is, 10.6. And you will see that it diverges, right? But we have to get there. So that's the first order of business, to understand that if something looks good with these guys, is not necessarily the answer, right? So let's learn the first one, geometric series. So, geometric. If you studied sequences ever, you know probably that there are arithmetic sequences and geometric sequences. And those sequences arithmetic sequence has this property. Your A2 is equal to A1, your AN. AN is equal to AN minus 1, so previous term, plus some difference D. So this is arithmetic sequence. Good example would be, let's say, start at 2 and keep adding 3 every time. So 2, 5, 8, 11, 14, 17, 20, and I'm bored. So your D is clearly equal to 3 in this case, and that's something that is called arithmetic sequence. So what is a geometric sequence? Geometric sequence is where your AN is some ratio R times AN minus 1. So you have a number that multiplies, always the same number. Could be fraction, could be whole number, could be whatever, right? It's always the same number that multiplies to get the next term. So let's use 3 and then times 2 every time. So 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48, times 2 is 96, times 2 is 192, and then go on. R equals to 2. I have been doubling this every time. So there is this notion of having R. Now guys, these are sequences. It's just a list of numbers with commas in between. Now, what is the geometric series? Geometric series. Geometric series, in this case, summation of AN, would be 3 plus 6 plus 12 plus 24 plus 48 plus 96 plus 192 plus ... going on to infinity. And then, when you put equal sign, all of these numbers going to infinity add to either infinity or a finite number for convergence. Now, are we going to sit there and add all of the numbers all the way to infinity? The answer is no, right? We're not going to sit there and add these things. So what should we do? We're going to learn the test which will help us solve these problems in less than 6 seconds. So what is the test? Geometric series test. Here we go. Yes, excellent. So geometric series test says, if you have a geometric series A, R to the n, where n starts at 0 and goes to infinity, this is the form that you have to have. So A, R to the n. So if you have that, you look at the R. If R is in between, -1 and 1, you have convergence. If R is outside of these bounds and 1, it diverges. This is called a test. It's on your sheet of paper on the second line. Now let's take a look at the way you use this thing, because it does look weird, right? Say that your geometric series is 3 to the n from 0 to infinity. You don't have to write n equals. We know it's n equals. So you can just say 0 to infinity. What is the solution to this problem? You use your eyes, you look at it, and you figure out that your r is equal to 3. That's bigger than 1. Diverges. And you walk away. That's it. So for geometric series, you extract r from the problem, and you look if it is between -1 and 1. If it is, it converges. If it's not, it diverges. So this is the entire problem. You say diverges by geometric series, by GS. Next example. Summation of 1/2 raised to the n, 0 to infinity. You look at it, you determine that r is equal to 1/2. Well, that's less than 1, converges by geometric series. There are no calculations, there's nothing. You either know and memorize this test, or you take a walk. It's very simple. No calculations. You just look at it. Let's take a look at summation of 16 divided by 3 to the n from 0 to infinity. All right, well, you gotta massage this one a little bit, because you see that n is only applied to a 3, has nothing to do with 16. So that means that I can write this as a 16 times 1 over 3 to the n, 0 to infinity. And then I'm going to write this as a summation of 16, and then I can also put 1 to the n. That's not going to harm anything. So now what I did is I did some algebra. Yeah, we can, but I'm keeping it in for a reason now. So now you look with your eyes, right, and you determine that r is equal to 1 over 3. That's less than 1, converges by geometric series. Now, what's this 16? When you look at the problem, it's a. So 16 is a. A equals 16. Now, that's just for a side note right now. We don't need it, so I'm not going to bother, because the next problem is coming up. And this problem says infinite series from 2 to infinity of 1 divided by 4 to the n. Okay. It's clear, hopefully, that r is 1/4, right? R is 1/4, and that's less than 1, and it converges by geometric series. Nice. Do we see any issues here? Excellent. We do see an issue that this is not a 0. Luckily, it does not impact convergence, which is good. But it's going to impact something else. And that is sum of this series. I haven't talked about that formula yet. See, we know it converges. It converges to a value. All of these numbers are adding up to a number. Which number? So there is a formula to calculate that. And if you look at your sheet all the way at the end in the comments section, it says that the sum of all terms is equal to a divided by 1 minus r. Very good. Now, we have to be very careful with that formula. So now here is the sum of geometric series S equals A divided by 1 minus R. If summation it goes from 0 to infinity, A, R to the N. So this is what you have. Okay. So, vanilla example first. Summation of 3 divided by 5 to the N from 0 to infinity. You immediately kick 3 outside, and this is the reason why you don't kick it all the way out, because you want to see that that's your A. And you go 0 to infinity. Now, you compare to see that you have the same form. Formula doesn't hold if your thing doesn't start at 0. If it starts at 1, starts at 2, that formula doesn't hold. You have to do work, and then you can use the formula. So we'll learn that. But let's do this example first. So just by visual inspection, we see that A is equal to 3 and R is equal to 1/5. Plug it in. All right? So S equals 3 divided by 1 minus 1/5. That's 3 divided by 4/5, which is 15 over 4. To me, this is fascinating that I get to add infinitely many numbers. Guys, I add infinitely many numbers and they add up to 15 over 4. Oh, come on. How cool is that?
Yeah, well, you have a fraction that's being infinitely exponentiated, so it's getting infinitely smaller until eventually it would hypothetically become 0, so you can add that up.
Yes, which is the reason why you are actually sitting on your chair right now, which is the reason why you actually got here. There is something that's called Zeno's paradox, which is a really interesting thing. You know it, right? It's a really cool thing. Zeno said this way: if I set up a target and shoot the arrow at it, you shoot the arrow, at some point arrow covers the half of the distance, and then there is still half to go. Now, looking at that half that it's left to go, the arrow is going to cover half of the distance of that half with another half to go. And then of that half, which is now a quarter, arrow still has half to go. So when Zeno thought of this 2,500 years ago, they didn't have limits or anything like that. It was really, right? Why would the arrow hit the target if there is always half of some distance to go? Right? How is that possible? Which is, right, interesting. Well, at that time, they did not have exponential functions. They did not have limits or anything to explain. Today we understand, obviously you would move if someone shoots the arrow at you, right? If I'm to just throw this thing at you, so you're going to move your head, right? Because you know what's going to happen. This is going to reach its target, plus my infinite strength. And yeah. And a perfect marksmanship.
There was something like that about like the race, Achilles versus the tortoise in the race, where Achilles always runs half the distance and eventually the tortoise wins because Achilles can't reach the end.
Well, that was the hypothetical thinking of that time. But if you have the distance that you want to cover, and then you cover a half, and then you cover a half, and 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 a half, right? So this is a half, this is a quarter, this is 1/8, because that's half of the quarter, and then 1/16 and 1/32. Clearly you are talking about sequence 1, 2 to the n. Now, what do we know about our sequences? You put the limit, shoot n to infinity, 1/2 to the n becomes 0.
It's taking its time today.
So, guys, going back to now my series, This is awesome thing, right? Because we are able to actually calculate what all of these infinite amount of numbers is going to add to. I need this. So now we see that the basic problems are not an issue because you just look what A is, you look what R is, you just plug in the formula, you're done. The issue is the problem we had before. Summation 2 to infinity, 1 over n to the fourth. It's definitely not cool to ask you what's A, because you're going to get it wrong, right? You're going to probably say 1, and I'm just going to say no. So, what is the issue here? The issue is this. That's the issue. Your form, which you memorize, is this. And clearly, it starts at 0. So now what we have to do is a mathematical procedure that you, if you're taking differential equations, you better know now, because you're just going to X out a chapter in DiffyQ. It's called shifting the counter. We have to shift the counter back to 0. Otherwise, no bueno. All right? So, here in blood, we have to shift the counter. We have to shift the counter. We have to reset that counter to 0. And now what is going to happen is the procedure for that. It's one of those like completing the square and stuff like that. Steps has steps, right? So you just learn it. Summation n equals to 2 to infinity, and then you can put 1/4 to the n. It's okay, right? So we just rewrite this, and I have to put now n equals to 2 because I'm shifting the counter. What am I going to do? Well, what my counter needs to be. And what is it now?
2.
How do I get to 0 from 2? By subtracting 2 on both sides. Good. This step changes depending on what you have as a counter, right? So now, what I have here is that n minus 2 is equal to 0. Do we all agree on that? N minus 2 is equal to 2 minus 2, that's 0. And I'm going to change the variable into a k. K equals n minus 2. So now, as I'm writing the new, this is k starts at 0 to infinity. Woohoo! Right? 1/4 raised to, can I have n now? No, I can't have n because we changed to k's. So now, what is my n from this formula?
K plus 2.
K plus 2. So that's my new exponent, k plus 2. Great. Hey, we fixed the counter. Did we? Yeah, we did, right? It starts at 0. What did we manage to mess up?
The end.
The end, right? Because your formula is looking for a 0 and n. What do you got? You got 0 and then n plus 2. K plus 2, right?
But that's equal to n.
It's not equal to.
Yes, you.
N minus 2 is equal to n, not n plus 2. Right? K.
No, you put right there. N is equal to.
Yeah, but I need this in k's now. Right? I need it in k's. So I need, if this is a k variable, then this has to be a k variable without a 2. How do I fix this? Please help me.
Nope.
It's a very easy fix.
Oh, yeah.
I peel off these two. Using basic algebra formula. Remember the algebra? x to the n, x to the m is equal to the x m plus n, right? Basic algebra formula we learned. So all I'm going to do now is I'm going to use that formula and say this is equal to summation 0 to infinity of 1 to the 4 squared and then 1 to the 4 to the k. So summation 0 to infinity 1 over 16 1 over 4 to the k, and there it is. We shifted the counter. Now counter is at 0. That's single up there. And what's my a? 1 over 16, huh? So a is 1 over 16. And r is 1 over 4. And now I can find the sum as 1 over 16 divided by 1 minus 1 over 4. That's 1 over 16 divided by 3 over 4. These guys cancel to the 4 and the 1. So it's 1 over 12, right? This procedure is called shifting the counter, and you have to do it every time. For geometric series only, maybe you want to write that down. Geometric series only is where you shift this counter to make sure that you have a 0 and that you have a single exponent so that you have a true representation of what A is. Your R didn't change. R is a quarter. We knew it was converges. We did it earlier, right? So we know it converges, but we wanted to calculate the number that it converges to. And it converges to 1 over 12. So as we add infinitely many of these numbers, they all together add to 1 over 12. And that's why we say it converges, because the sum is a finite number, in this case, 1 over 12. So this witchcraft, right, is to be performed only on geometric series when your counter is not 0, right? You should have that stuff on at least one of your exams. You should have this stuff at least 1 or 2 problems on the lab, right? The homework. So shifting. And by show of hands, how many of you are going to differential equations? Yeah. I was. Guys,
I'm gonna get past this class, much less.
Oh, yeah.
to solve differential equation, you have to differentiate power series, which is our chapter 11. Every time you differentiate a power series, your counter goes up by 1. So your function starts at 0, your first derivative starts at 1, your second derivative starts at 2. So if you have a second order differential equation to solve with power series, you have 3 things to worry about, and they all start with a different counter. You can't push them together until you shift the counter. That's your chapter 3 on DFQs. So no messing around, right? No messing around. You have to know this if you are going, you have to know this procedure of shifting the counter if you're going to DFQs. It's very simple, right? You can obviously rewind the video a few times and get the stuff. The process is always the same. You subtract whatever you need to bring down to 0. You define that to be your new variable k, and then you just plug everything in and then peel off extra exponents to bring this to a single variable. And then you have k starts at 0, and you have k, and then at that point you can just go on and record. So this is the most important stuff over here, right? That's the stuff that does the transformation for you. We are done with geometric series. This is it. You have to learn the test, and then all you do for convergence or divergence is you look at R. Is R between -1 and 1? Yes, converges. No, diverges. If it converges, you can calculate the number, right, the sum, to which it converges to. And in our case, that was easy to perform in the first example. where we just said, okay, A is 3 and R is 1/5, plug everything in, you're done. Second example, not so easy, not so pretty, because the counter was shifted. So we had to shift the counter back to 0, and then use once everything was done, right, then this part is easy. You just pick your A and R and plug in the equation. So this closes the book on geometric series. The next one in line are telescoping series. Your book is barely touching on these, but they do have, I noticed they do have some examples, and they do have homework on it. I believe the book does only one example or 1.5 examples, whatever. The form is b to the n minus a to the n. So you have a subtraction. And I hate to start this at any number over here. I don't want to put this because then it looks like a big fat 0. It can start at 2, it can start at 7, it can start at any. Geometric series are the only ones that are, you can actually add that if you want in a box with geometric series. They are the only test out of 10 tests that are sensitive to start at 0, okay? All other series, they can start at 1, 2, 3, nothing. You don't have to shift, right? So the only shifting you are doing is shifting in geometric series because they're sensitive, okay? They have to start at 0. The rest can start at any number and go to infinity, and we will not have to shift anything. So telescoping can start at 1, can start at 2, can start at 3, can start at 0. Right? Yes?
Can you have a series that's fixed, right?
Yes. Sure. Right?
How would you treat that?
Because it's sum, so you just separate them in each one individually. If they both converge, then the whole thing converges. If one explodes, then the whole thing is gone. Well, you are adding them, right? Because the series would be combined in some way. Series times series, if they're right. We're going to learn very quickly that you will only know the convergence for geometric and telescoping. That's why they're first to learn. You will only be able to tell that it converges to 7 or converges to 2 for geometric and telescoping. The rest, 8.
Just converges.
Yep, and you don't know what to. Diverges, obviously infinity, but converges, and you don't know what they converge to. That's where you come in with your 10,000 or 1 billion terms, right? With a loop, with a for loop. Yeah. The while loop, while power is on, right? That's the variable in the parentheses. There you go. Keep adding, right? See what happens. All right, telescoping series, guys. Row number 3 in your gift, telescoping series. Now, I use the BN and AN, and they're using BN and BN plus 1. Fine. We can use that notation as well. You will recognize telescoping series when you see a minus sign. Is that obvious? There's a minus sign there. So there are no formulas here. It's just a procedure, which way we deal with the telescoping series. So lock the doors.
I was just going to say there's no n.
Well, as I said, you can start n at any number, or at 1 or at 0 or whatever. So that's why I didn't write anything there.
Oh, well, here's.
Yeah, they said 1, but so they can have b1 minus b0, just the first 2 terms. But I know they're stuff, stuff is like that. All right, let's learn the procedure, guys. Summation. We start at 1, go to infinity for 1 over n minus 1 over n plus 1. converge or diverge. All right, so these problems are a lot of writing. I'm tempted to change something, but let's not. All right, so this is what I'm going to do. I am going to write. I'm going to start writing these terms out. And look at the pattern, and hopefully some stuff will work out. So let's see. The first one is 1 divided by 1 minus 1 divided by a half. Do we all agree on that?
Mm-hmm.
For the first term, I plug in 1, and this is what I get. Plus, now the next number that I have to use is n equals to 2. So plug in that. That's going to be a half minus a third. Plus, now I have to use 3. That's going to be what? A third minus a quarter. Plus, quarter minus a fifth for n equals to 4. And I'll write one more. Plus, 1 is 1/6 for n equals to 5. Plus 3 dots. Now, what's happening on the tail end?
They keep canceling each other out. Negative a fourth plus a fourth. Negative a fifth plus a fifth.
Oh yeah, we'll get that. That's exactly what's happening. But what I want to do now is I want to write, you see how I have like infinitely many terms there, right? That I'm not writing out. If I am going to replace these n's with a finite k, so I am replacing n with a finite k, and then I'm going to send the k to infinity. Remember how we did that for our improper integrals? You took your infinity, you replaced that infinity with a finite value b, and then you send b to infinity in the limit, right? Do we all remember that? I did that problem at the beginning of the class, right? You had the infinity, let's say 2 to infinity, and you did limit 2 to b, and you send b to infinity. Now, for these guys, instead of using summation n goes from 1 to infinity, I'm going to switch my k goes from 1, n goes from 1 to k, and then I'm going to stick the limit and send k to infinity. It's the same thing, same idea. Are we all agreeing on that? All right. So what I'm going to do now is I'm using k's. Let's write at least 3 terms. The last term is always equal to the problem is just now with k's because I switched that out, right? I'm making it finite. The last term is always the same as the problem, and now the term before is minus 1 on each k, and the term before that is minus 1 again, so k minus 2 minus k minus 1. Well, yes. So, and that's exactly where they die. So, do we all see what just happened here? I started with n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. I am ending my infinite series by turning it into a finite series with n equals k minus 1, n equals k minus 2. So now these are finite terms. I can pick k to be 100 or 10,000 or whatever, right? So I turned my infinite series into a finite series, and then what I'm going to do is I'm going to send k to infinity. The same hack that we used for infinite series, for improper integrals, sorry. All right, so what do I have here, guys? Do we all see that halves cancel? And the thirds cancel? And the fourths cancel? And the fifths cancel? It's reasonable to assume that 1 over 6 will cancel as well, right? Look at the back end. K's 1 over k gone, 1 over k minus 1 gone. Well, then this one is going to cancel as well, right? Do we see that everything canceled? What's left? 1 minus the limit of k goes to infinity of -1 over k plus 1, right? Well, isn't this going to 0 now? Because it's 1 over infinity? Yeah, right? So as this shoots to 0, good one. This is equal to 1. Right? Equals to 1. Now I want you to look at this and just realize that someone figured this out. Yeah, it's 200 years old. All right, this calculation is at least 200 years old, but
That's because they had no cable, they had no phone.
exactly, no cable, no phone, no distractions. You just sit there and say, all right.
Yeah, but at least like make a baby over this crap. You know what I mean? Oh.
But then you got
They used to make 10 babies, 15 babies because they were dying. You know, there were no vaccines that time,
Yeah.
right? Now we have people voluntarily killing their kids by not vaccinating, right? At that time, they didn't have a choice, right? That's not funny. That's not funny.
As long as they volunteer to kill their own kids in their own school. That's all
Yeah.
I care. Just as long as
It's
you don't
worse
put
than a
your kid in
witchcraft,
my
right?
school.
In the old age, right? Now they say, okay, get a kid and rub an essential oil into it.
It's all about the
Really? That's gonna help? With polio? No.
CBD oil.
Yeah, I
Yeah,
know.
that's CBD oil.
That's another word everywhere.
200 years of medical research, right? It is Susan on the phone, like browsing the internet. Yeah, I don't think I'm gonna vaccinate my kid. You know, I did my research for like 2 hours. Anyway,
Dumbasses.
exactly, dumbasses. That's. Anyway, all right, let's go. And what else do we have? Let's take a look at the book for another example of this.
I don't need it.
They just sent the wrong RX.
How don't you go nuclear over that stuff? Like, I don't understand. In your textbook, I think all the editions only had like 4 or 5 exercises. Now they have 54 to 69. That's like 15 exercises at least, right? And they have a lot of cool ones. The first 2 out of 15 look like this. First 2. Now, what are the other ones? Look, what the other ones look like? Other ones look like this. Lock the doors.
Do you think
Summation?
those
No.
examples are the same as my math lab?
Yes.
Oh my God, imagine taking a quiz.
Or do you think
test
it's
on this crap.
harder? Oh, this is easy.
Oh, this is gonna be fun.
Does this look anything like your BN minus AN? No, it doesn't.
You weren't buying that.
I don't like it.
So, partial fraction decomposition. There we go.
Yeah, you finally got one.
13 problems. 13 problems of partial fraction decomposition just to get it into the form so that you can do this. I know. All right, partial fraction decomposition. We're technically reviewing for the test now, right? Because partial fraction decomposition is on your exam. So let's do partial fraction decomposition here. What do we have? We are separating this into summation of a over k plus 6 minus b over k plus 7. By the way, this book like k's. For some reason, most of the civilized world is using n's. So doesn't matter which letter you use as a variable. It's just the problem is that I eventually switched to n, like half problem, because I just can't get used to k. Anyway, partial fraction decomposition. So we have ak. Like you start with the ak.
Plus this. Okay.
Plus 7a.
7. Okay.
Yeah. Minus bk. Minus 6b.
Oh, I got you.
Is equal to, well, yeah, I'm cross multiplying, killing denominator.
Yeah,
We'll just,
I got you.
we'll just fly through this. Okay, so now we have
BK.
a minus b k plus 7a minus 6b equals to 0k plus 1, right? So I am matching red with red and blue with blue. My red equation is a minus b equals to 0. And this one is 7a minus 6b equals to 1. Excellent. Now, whatever witchcraft you can pull off on this one, right? Substitution, elimination, guessing, essential oils. Whatever works. You rub some essential oils into this problem and just the problems like that, A and B. This is too much. Anyway. All right, so when I multiply by negative 6, that will kill b's. I have a is equal to 1. Nice. Right? It's going to be negative 6a plus 7. So if a is 1, b has to be 1 as well. Because a minus b is 0. Great. So now I have my series. It's 1 over k plus 6 minus 1 over k plus 7. We are starting at 1, going to infinity. So plug in 1. That's 1 over 7 minus 1 over 8. Plus 1 over 8 minus 1 over 9. Plus 1 over 9 minus 1 over 10. Plus 1 over 10. Are we bored yet? Minus 1 over 11. Plus dot, dot, dot. Now we start on the tail end. So over here. Now we have to use n's. So 1 over n plus 6 minus 1 over n plus 7. Take away 1 for the term before. 1 over n plus 5 minus 1 over n plus 6. Take away again 1. So 1 over n plus 4 minus 1 over n plus 5. It's a pattern. 8 kills 8. 9 kills 9. 10 kills 10. 11 will die here. 6 and 6, 5 and 5, 4 will die in here. Yeah, and I don't like this problem because it worked out that way again. So
It doesn't work out like that all the time?
nope.
Oh.
Nope.
I thought it was
So
a
you
pattern.
write out the pattern.
So 1 over 7 minus the ln limit of n goes to infinity of 1 over n plus 7. Now that dies. And the answer is just 1 over 7. All right.
Oh, I thought it always came out like that.
That solely depends on how far apart these are. N plus and k plus 6, k plus 7 are 1 apart. So they're going to start canceling immediately. When they are 2 apart, or 3 apart, or 4 apart, they don't start canceling until later. Yes?
So, how do you, like, you ended with 1 over n plus 6 minus 1 over n plus 7, but how do you know when to stop?
Well, this is the last term that is finite, and it's always the same as this one, just with a finite variable. And then you just keep subtracting 1 for each one before.
So, but you're always, the answer you're always going to be in the first number, 1 over 7, the other one was 1 over 1.
That's what I want to do now. Guys, in the last 4 minutes of the class, in the last 6 minutes of the class, thank you very much, we are going to take a look at a problem that it's not the same as the previous ones. So now, I'm going to have a summation of 1 over n minus 1 over n plus 3
Every third they're gonna cancel.
from 1 to infinity. So what happens now? Well, as I start writing this out, luckily I don't have to do partial fraction decomposition on this one, right? What do I get? I get 1 over 1 minus 1 over 4 plus, what do I get in the next one? 1 over 2 minus 1 over 5. Does anything cancel?
Not yet.
No.
On the next one.
Not yet. Very good. Plus 1/3 minus 1 over 6. Nothing is canceling.
It should now.
Plus 1/4 minus 1 over 7.
That's where it starts.
That's where it starts canceling, right?
Yep.
The next term plus 1 over 5 minus 1 over 8 plus 1 over 6 minus 1 over 9 plus 1 over 7 minus 1 over 10 plus 1 over 8 minus 1 over 11. Do you think that I particularly enjoy writing this out? No. But what's happening here? When you start canceling, where's my red pair? Negative quarter and positive quarter, gone. Now, you can also see, here's the purple, these are gone. So now, I need a 6, let's do the blue one, a 6 and a 6, gone. And here is finally what I was looking for and waiting for. 1 over 7 with 1 over 7. This is the first time when both cancel. As soon as you hit that one, everything after that is guaranteed to cancel. So now look, you see that 1 over 8? There it is, right? So as soon as you hit the first parenthesis that cancels both terms and you see it, that is when it starts canceling to the point where you can just drop everything else. So now what is left? It's 1 over 1 plus 1/2 plus 1/3. And your limit at the back is going to have 3 left because it always mirrors the front. Right? So now the tail end is going to leave, as a mirror image, it's going to leave the terms, the last one, then the skip in the next parenthesis, the last one, and the next parenthesis, the last one, and everything else in a mirror cancels as these ones do. How many of these do you have to write out? When is your first parenthesis that cancels everything? How far apart are these?
3.
3 terms. 1, 2, 3. And then 1 canceled in. What was the first problem? n plus 1. How far apart were they? 1. So when was your first canceling both? Second term, right? This stayed and this one was canceling both immediately. The separation between those, when you have these vanilla problems, n and n plus 3, Does it hold when it's 2n plus 3? 2n and 2n plus 3? I'll let you figure it out when you go home with it, because you have homework assignment on it, right?
Okay.
So you know the procedure, right? All you need to do now obviously when you start this, right, first do some, right? These problems are excellent for killing time and carpal tunnel and,
What you're gonna do when you put you know how you put a fraction in front of your limit? You're gonna
Yes.
do add 1/1, 1/2, and 1/3 together to make that into one fraction.
Yes.
Okay,
And then you say converges to that number.
okay, I got you.
And the tail ends are all gonna drop.
I learned it at home.
However, guys, I forgot to tell you, I have 30 seconds. These problems can also diverge, and we haven't seen an example of it, but when you run into a square root or ln, they might diverge, all right? So there will be those examples in the book as well. I just didn't get to them.
Next class.
We could.
Here,
Bye.